Maigovanin, folks. Today we have quite an interesting video. The thumbnail seemed quite interesting, and you may be thinking, was that just clickbait? Well, technically it wasn't, because you're about to learn the Mellin inversion theorem. That's right, we're about to prove it. So I think that's a fair trade. You see a crazy sort of integral on a thumbnail, you click it, and you have the Mellin inversion theorem. Yeah, sounds like a fair trade indeed. So what is this theorem, or this result? Well, say we have a function f of x, and we're interested in its Mellin transform. So we'll call that psi of s, the Mellin transform, of course, being a function of the complex variable s. And this psi of s function needs to satisfy certain criteria. So psi of s is analytic in the strip real part of s bound between a couple of real numbers that we'll call s sub 1 and s sub 2. And psi of s, sorry about that, psi of s approaches 0 as the imaginary part of s approaches positive or negative infinity. Okay, cool. So if you have such a function psi of s being the Mellin transform of a function f of x, then we can invoke the Mellin inversion theorem for any real number a between s1 and s2. We have f of x equal to the inverse Mellin transform of the function psi of s, and it will be equal to 1 over 2 pi I times the integral from a minus I infinity to a plus I infinity of x to the negative s times psi of s ds. Okay, cool. So for the proof, the first thing we'd like to do is write out the Mellin transform in the integral form. That is, we know that psi of s is defined as the integral from 0 to infinity of x to the s minus 1 times f of x dx. And now we'll introduce a nice little transformation by letting x equal e to the t, which implies that dx equals e to the t dt. Also, this means that t equals log x. So as x approaches 0, terribly sorry about that, we have t approaching negative infinity, and as x approaches infinity, we have t approaching positive infinity. So that means psi of s equals the integral from negative to positive infinity of e to the t to the s minus 1, which of course can be expanded as e to the ts times e to the minus t times f of e to the t, whatever that means, e to the t dt. Immediately we see this nice cancellation. So our integral transforms into that from negative to positive infinity of e to the ts times f of e to the t dt. Now we know that s here is a complex number, so we'll expand it in terms of its real and imaginary parts, and we'll write s as a minus I times b. Now for the purpose of this proof, the writing of s as a plus I times b would be equivalent, but this is just a little bit nicer, and you'll see why in a while. So psi of s equals integral negative to positive infinity of e to the a minus ib times t times f of e to the it dt. Finally, we have the integral from negative to positive infinity of e to the at times f of e to the t times e to the negative ibt dt. And this integral form seems pretty familiar. It looks exactly like a Fourier transform, and that is exactly what we have. So the Fourier transform of a function f of t as a function of b equals the integral from negative to positive infinity of f of t, terribly sorry about that, times e to the negative ibt dt. Okay, cool. So this implies that psi of s is just a Fourier transform. It is the Fourier transform of the function e to the at times f of e to the t, and that means e to the at times f of e to the t is the inverse Fourier transform of the function psi of s. Of course, the left and the right-hand sides are functions of t. And the inverse Fourier transform is given by 1 over 2 pi times the integral from negative to positive infinity of our function psi of s times e to the ibt db. Okay, cool. So we have e to the at times f of e to the t on the left, so we'll expand the entire thing by e to the minus at. And this means we have f of e to the t equal to 1 over 2 pi times the integral from negative to positive infinity of psi of s times e to the minus at plus ibt. So we'll factor out a negative t variable, leaving behind a minus ib db. Now, we know that s here equals a minus ib, so we might as well express the integral in terms of s rather than b. So this means that ds equals negative I db, terribly sorry about that. And this further implies that db equals ds over minus I, which implies that f of e to the t equals 1 over 2 pi times the integral from a plus I infinity to a minus I infinity now, because s equals a minus I times b. So we have psi of s times e to the minus s times t ds. But wait a minute, we still have a t variable in there, but we can get rid of it since we have e to the t to the minus s. And recall that e to the t is just x, which implies that f of x equals, oh wait, terribly sorry about that, I forgot the minus I over here. So we have 1 over 2 pi I with a negative sign. However, if we switch up the limits of integration to be a minus I infinity to a plus I infinity, we get rid of that extra negative sign. So we have 1 over 2 pi I times the integral of e to the t is x, so we have x to the negative s times psi of s ds. And that, my friends, is the Mellin inversion theorem. But now, what about that integral on the thumbnail? Now, this is going to be quite an interesting discussion. It starts off with the gamma function. What is the gamma function? Well, gamma of s is the integral from 0 to infinity of x to the s minus 1 times e to the minus x dx. Now, this thing looks exactly like a Mellin transform for e to the minus x. So we have Mellin transform of e to the minus x equal to gamma of s. Okay, cool. And we have the Mellin inversion theorem, which implies that e to the minus x equals 1 over 2 pi I times the integral from a minus I infinity to a plus I infinity of x to the minus s times gamma s ds. That looks fun, but immediately we run into some red flags. The question of the asymptotic behavior of the gamma function, and of course, where is it analytic? We know that the gamma function has simple poles. For s, its argument, that is, s equal to any non-positive integer. So I'm going to do a bit of a detour here for the gamma function to actually work out a solution development. And this is going to be pretty interesting, and I realize I'm walking a pretty tight rope here, but it's fun. So we have the reflection formula gamma z times gamma 1 minus z equal to pi over sine of pi z. Now, what if I were to let z equal to I times x, where x is a real number, meaning that z is purely imaginary? So gamma ix times gamma 1 minus ix equals pi over sine of I pi z. Now, what exactly is, terribly sorry about that, gamma of 1 minus ix? By the recursion formula, this would be minus ix times gamma of minus ix. But minus ix is just ix conjugate. And we know that gamma of z bar equals gamma z bar. Straight up mathematical bars here. So that means we have gamma 1 minus ix equal to negative ix gamma ix bar. Okay, cool. So all of this implies that we have minus ix times gamma ix times gamma ix bar equal to pi over the sine of iz equals I times the hyperbolic sine of z. So we have sinh of pi z. And what on earth is z times its conjugate? That is just the squared modulus. So we have minus ix modulus gamma ix squared equal to pi over I, but 1 over I is just negative I. So we have sinh of pi z. Oh, terribly sorry about that. I kept writing z instead of x. So yeah, my bad. And what does all of this finally mean? It means that we can cancel out the negative I terms. And we have absolute value gamma ix squared equal to pi over x times sinh of pi x. Again, terribly sorry about that. And this is pretty cool, because it shows that this thing does indeed approach 0 as x, that is the imaginary part, approaches plus or minus infinity. But there's another problem. For gamma s, if we were to take the real part of s equal to 0, we run into problems regarding its analytic behavior. It's no longer analytic in the strip where we're trying to calculate the integral. So that is a problem. So we're going to have to work with a limiting argument here, or a limiting case of the limit of absolute value gamma a plus ix as a approaches 0 from the right. This thing equals root pi over x times sinh of pi x. Thank you, continuity of the gamma function. And this thing does indeed approach 0 as x approaches plus or minus infinity. Okay, cool. This is awesome. This is awesome so far. Again, I'm walking a really tightrope here, but this is absolutely beautiful. And for the subsequent calculations, bear in mind that this limit is just attached everywhere, so just picture that in your mind, guys. We have, again, e to the minus x equal to 1 over 2 pi I times the integral from negative I infinity to positive I infinity of x to the minus s times gamma s ds. And of course we have s here equal to I times t, which implies that ds equals I dt. So e to the minus x equals 1 over 2 pi I times the integral from negative to positive infinity of x to the minus s. I'm going to leave it like that for now. And we have gamma of I times t, I times dt. And the reason I didn't bother to even expand the s upstairs in the exponent of x is because, well, we're going to cancel it by letting x equal to 1 anyway. So we have e to the minus 1 equal to 1 over 2 pi times the integral from negative to positive infinity of gamma it dt. And this implies, yeah, I should probably write the limit explicitly now. The limit, as a approaches 0 from the right, of the integral from negative to positive infinity of gamma a plus it dt equals 2 pi over e. This was insanely cool. Math is beautiful. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.